I think we may now start. I think lots of people joined after this new link. So welcome everybody. Good morning. Just to apologize for this delay in the starting process, but we are having a lot of issues regarding to enter the team session. So we have to postpone it and create a new link so everyone could join. I think now we are stabilized and ready to start. Just one more people entering. Just let me welcome everyone and thank you for joining us today. We're glad to have you here for this webinar on Introduction to Parallel Performance Engineering as part of the EPICURE project. I want to thank Ilya and Michael for being available to give this webinar. We hope you enjoy the session and find it insightful and engaging. During the presentation, you may ask questions in the chat if you want, or even in the end. And when the presentation ends, I think Ilya and Michael will have a few minutes to answer your questions. Let me just introduce Ilya and Michael. Ilya is a senior HPC consultant at the Jülich Supercomputing Center with over 8 years experience in supporting users of large HPC systems. He's been closely involved with the POP, the COE, the CIV, GCS, and EPICURE projects at Jülich Supercomputing Center, providing hands-on support to researchers across diverse scientific domains. His primary focus is on helping users exploit HPC systems efficiently and to improve the performance and scalability of their application, thus being presenting this webinar, one of his main topics of work. Michael obtained his PhD in mathematics from Technical University Dresden in 2008, and then he joined Jülich Supercomputing Center, where he worked as a HPC performance engineering. His research interests includes, but not limited to, performance and energy consumption analysis of large HPC systems and applications, and the development of corresponding tools. He is an active member of the MPI forum and regularly gives courses about parallel program and performance analysis. Ilya and Michael, thank you very much for your availability for this webinar, and now the floor is yours. Thank you very much.
Okay, so I guess I start, Ilya?
Yes.
Thanks for the introduction. And today, Ilya and I'm going to talk to you about a very brief introduction to parallel performance engineering as a first part of this series of webinars. Okay, let's get started. Performance really is an old problem. And by the way, I'm the only one for whom the slides are blurred. I basically can't see anything, but I know them. I created them, so that's not an issue. But if you can't see the slides correctly, please let us know. We can hopefully find a solution, but it might be just for me. Anyway, as I said, performance is an old problem. And this picture here, we see the difference engine, one of the first mechanical compute machines proposed by the British inventor Charles Babbage in the 1820s. And during his lifetime, he actually never built one. But fun fact, this was the machine that Ada Lovelace programmed the first applications for, right? That's why she's considered the first programmer on a machine that never existed in their lifetimes. However, he said that the most constant difficulty in contriving the engine has arisen from the desire to reduce the time in which the calculations were executed in the shortest which is possible. And incidentally, that is basically the definition of supercomputing that we still have today, right? We want to calculate calculations as fast as possible. And for a long time, performance gains came for free, right? With the introduction of integrated microcircuits on microcontrollers. Basically, we had Moore's law, which says that the number of transistors on a compute chip doubles every 18 months. And for a long time, that just meant that we gained double the performance out of that. However, for a couple of years, this is not true anymore, right? So Moore's law is still in charge, but the clock rates do no longer increase. So basically, since the 1990s, early 2000s, we have more or less constant clock rates, even decreasing clock rates on modern day processes, right? But these chips become more complex because, as I said, Moore's law is still in charge, but we only get performance gains through increased parallelism on chip and off chip, right? That makes optimization of applications running on modern day supercomputers more and more difficult by the decade, right? So this has multiple reasons. First is we see an increase in application complexity. Though many of the applications run on our supercomputers are developed over many, many years, right? And they become more and more complex. We see a lot of multi-physics codes nowadays. We see a lot of multi-scale codes. And those all of these things have to work together efficiently in order to gain performance out of the system. But not only the applications get more and more complex, the machines get more and more complex by itself. So we nowadays have hierarchical network topologies. We have memory hierarchies, right? We have many core CPUs and accelerators. As I said, we have increased parallelism on chip on a single CPU. So nowadays we have 96 cores on a single CPU, right? That was unimaginable a couple of years ago. And we have a variety of accelerators, namely GPUs from NVIDIA and AMD. We have some FPGAs and what else is out there, right? And one specialty in Jülich, we have this modular supercomputing architecture where we combine a general purpose cluster and a highly scalable booster that can be used together. So making efficient use of these machines is difficult. And if you scale up, typically in your application, a new bottleneck arises whenever you double your scale you're running. Right, so this is something you have to keep in mind. Okay, next slide. So for performance engineering, we regard a couple of performance factors, as we call them, and those can be distinguished in sequential performance factors. So those are things you have to consider even when writing a sequential program. So you don't use any parallelism to begin with. In fact, you have to use some parallelism to get performance because your single core, right, still is kind of a parallel computer. So you have to deal with all the effects that arise from that, with pipelining, with out-of-order execution. So, right, you have to choose a right algorithm that can benefit from these processor features and use an optimizing compiler. So always compile code for the architecture you're running on, right? Otherwise, you waste a lot of potential performance. Another very, very important point is vectorization. Right now, basically every processor has a vector unit attached to it that is responsible for most of the potential performance of that processor. Right, so you can basically do calculations on 8 values simultaneously. If you don't use vectorization, you basically waste 7/8 of the potential performance of your chip. Right, so keep that in mind. And if you want to make efficient use of the system, use vectorization. Again, choose an algorithm that can be vectorized and use a compiler that actually generates vector code. And the final thing you have to deal with when writing sequential code is actually caches and memory. So make best use of the memory hierarchies that's available to you on your system. So you basically hide the latency of memory accesses by making efficient use of caches. So you have to make sure you use the right data structures and data layout in order to get that. Okay, next slide, please. And then that's not worse and enough. It gets even worse if we look at parallel performance factors. So those are the things you have to consider when going multi-core, multi-node. Right? The first thing and the most important thing is the partitioning or domain decomposition. So you have to make sure that the load balancing of your application is efficient. So what you ideally want to have, and we discuss this in the next parts of this webinar, is you want to have that every compute entity has the same amount of work to do between two synchronization points, right? So this is what we call load balancing. And you have to consider communication. So you need to transfer data between processes. You have to regard multi-threading. You have to look at core binding and NUMA issues. So make sure that you don't have to access memory that is located on remote memory. You have to look at synchronization and locking to write efficient and correct codes. And one important factor that's often not given enough attention is parallel I/O. And parallel I/O really matters at scale. So you won't be able to write a scalable application if you rely on sequential I/O. Okay, so next slide. A couple of tuning basics. Before you actually start using tools, you should set various tuning parameters very carefully, right? First thing is use the right algorithm and libraries. Libraries are important. There are many smart people writing highly efficient libraries. So don't reinvent the wheel. Use libraries if possible, right? And use the correct algorithm. If you write your application using a bad algorithm, you can tune as much as you want. You won't get an efficient result because if your algorithm is bad, you're out of luck, right? As I said, use compiler flags and directives. So produce code that actually matches the platform you're running on. So use the optimization flags. Make sure the compiler generated vectorized code. And if not, have a look at why not, right? Get the machine usage right. So look at mapping and bindings. So make sure that you don't suffer from these NUMA issues. Tools will tell you in the end, but it will cost you a lot of time figuring this out, right? So get the most performance or the best system usage before starting your analysis, right? Next thing, Leah, please. And keep in mind that always measurement is better than guessing. So if you want to determine your performance bottlenecks, so don't just say, oh, my kernel X is my main bottleneck. Measure and verify that this is actually true. And if you want to compare alternatives, so you have basically two algorithms you can use for your application. You have both implemented and you want to check which one performs better. So in points, you can measure that and validate. And if you actually did some tuning, validate your tuning decisions and optimizations by measuring, right? So don't guess. And this is important. Please do that after each step. So we have a lot of codes that added OpenMP statements to their MPI codes, a lot of them, and in the end did their measurement and found out, oh, well, my code performs worse than before. So why is that? I mean, OpenMP has some overhead by its own, and then we had to look at hundreds of OpenMP statements and see where the performance degradation came from. So please do these things after each step, or at least each couple of steps, right? Okay, next thing, the performance engineering workflow. So what do you have to do in order to get do performance engineering? The first thing you need to do is you prepare your application, usually with some symbols or insert extra code. Easiest thing is you just compile with -g, so the adding debugging information, so that way the compiler already does something for you. Or what you can do by yourself, easily enough, is just add printfs with some timers, right, to get easy instrumentation. Next thing is you measure, right? So you collect the data relevant to the performance analysis you want to do. So you gather data, right? With the data that you have, you can, next up, please, Ilya, you can do an analysis, right? So you first is you get some data, and then you calculate metrics of interest. You identify the performance metrics that you want to use, and those performance metrics can then be, next thing please, examined in a tool of your choice, right? So you present the results of the analysis in a hopefully intuitive or understandable form. And with that, next thing, what you have to do is, of course, optimize your code, right? So you identified your bottleneck, you know what to do, or maybe. Then you have to optimize it. So eliminate or reduce the performance problems that you found with the performance analysis you did before. Unfortunately, this is a step where the tools don't help you with, right? So tools help you with the first 4 steps, but there is no magic tune my code button in any tool that I'm aware of, right? There are some hints on what you can do in many of the tools, but no tool will be able to fix your code for you. And of course, this is an iterative process. So whenever you fix a bottleneck, you can basically tackle the next one. However, next slide, please, Elia. There is this what we call the 80-20 rule, right? So this says that programs typically spend 80% of their time in 20% of the code. So you really should know which part of the code matters for execution time. And developers typically spend 20% of their effort to get 80% of the total speed up possible for the application. So you have to know when to stop, right? So you can always try to squeeze out another percent in runtime, but it's simply not worth it typically, right? Because you simply can't gain much. And don't optimize what does not matter. So if your code can take different code passes depending on the input set, focus your performance analysis and the tuning on those parts that are actually exploited by your large production runs. Right? So if you use a small test case for performance analysis that takes a different code path than your production run using a larger input set, you tuned the wrong thing, right? So your small run might be faster than before, but your production run still takes the same time because you didn't tune what actually matters. Right? So be aware that you actually focus your tuning on what's impossible. Okay. Next thing. So what are some metrics that we are looking at? So we can measure a lot of things, right? We can measure counts, how often a certain event occurs. For example, the number of MPI point-to-point messages that were sent. Then we can measure the duration of an interval, right? For example, the time spent in these MPI point-to-point messages that we just counted. And we can measure sizes of parameters. For example, here, the number of bytes transmitted by these ports, right? So we know for the MPI point-to-point messages then how many messages were sent, how long it took, and how many bytes were transferred, which is quite some information. But of course, that's not sufficient. So what we need to do is we need to create derived metrics out of them. Earlier, next thing, please. So once we have these single metrics that we can measure, we can use these things to create derived metrics. So we can, for example, compute rates, for example, flops, so floating point operations per second. We can calculate some throughputs, for example, through network or memory hierarchies that we have. And this is needed for normalization, right? With single measures, we get a quantitative analysis. So we know exactly how much happened. But if we want to have a qualitative analysis, we need to create derived metrics. So for example, we are interested in what kind of what amount of peak performance did we reach, right? We know our system is capable of 1 exaflop, and we reached, let's say, 800 teraflop, which is really, really bad. If we reach 800 petaflop, we are quite good, right? So we need to know for normalization some derived metrics that we need to create. Okay. However, that's not as simple as it sounds, right? A couple of example metrics that we have is execution time. This is more or less straightforward, right? Number of function calls, it can be counted. If we go deeper on a processor level, we can calculate the cycles per instruction, so CPU cycles it took for an instruction. However, for that, in order to make sense out of that information, you already need to know what's a good value for your processors that you have. there are processes that can actually do 4 instructions per cycle. So if you have 1 cycle per instructions, that's not necessarily a good thing, right? Because you can basically get a quarter. So to make sense out of this information, you need some knowledge of your hardware. Looking at flops, as I said, the floating point operations executed by second, things become even worse, because what do you actually calculate? Your next thing, please. Right? So this can mean many different things. Are those math operations? Are those hardware operations? Are those hardware instructions? Because that can be different things, right? So we can have a division. That can be probably one hardware operation, a div. However, those are multiple hardware instructions, because you can't do a div in a single instruction, right? Do you count 32 or 64-bit instructions or operations or whatever? Because that will give you different numbers, and you have to make sense out of numbers. So you need to know exactly what you're actually measuring in order to make sense out of the information that you got. Okay. Execution time, as that is an easy metric. Well, it kind of depends, right? So what do you actually measure? Is it wall clock time? So this includes waiting time for I/O, for memory, for other system activities, right? So your operating system might need to time slice your application. So some operating systems things comes in between your actual application time. So if you count wall clock times, this time is included. The times you wait for memory to become available is included. Right? If you only count CPU time, this is the time spent by the CPU to actually execute the application. But this does not include the times the program was context switched out. And the problem is it does not include the inherent waiting times, for example, for I/O. And another problem that arises if you just count CPU time is the problem of portability. So on different systems, it's handled differently, what is considered user and what is system time. And another problem that we are facing is that execution time is non-deterministic on basically every modern supercomputer. Right? So you will always have some run-to-run variations. In the good old day of the Blue Gene supercomputers, and I'm not sure any one of you is old enough to remember, we really had more or less deterministic execution times. That were nice days. Those have passed, unfortunately. So if you do performance analysis, that means do multiple measurements and use the mean or minimum of several runs in order to get a reasonable information on the times it actually took you to execute your application. Okay. And another thing we have to consider are inclusive and exclusive values. So what we mean with that is inclusive means this is the information of all sub-elements aggregated into a single value. Right? And exclusive means information cannot be subdivided further. Looking at this simple example here, we have a function foo that does some computation, calls a function bar, does some computation again, and returns. So inclusive time is everything that happens within this routine foo, right? And if we want to have the exclusive time, we basically just count that we cannot subdivide further, though all the direct computations done within foo, and we exclude the time taken in bar, because this can be subdivided further into a new domain of bar, right? So this will become important when looking at the tools later on. And with that, I'm probably done, and Ilya will go into a classification of measurement techniques. So go ahead, Ilya, please.
Yeah, thank you, Mikhail. So now I'll talk about measurement technique classification. Basically, you can subdivide it in 2 dimensions. First is when our performance measurements is triggered. And there are 2 ways to trigger the measurements. First one is external trigger, or it's also called asynchronous. So it's basically called outside of your own application. So that's why it's asynchronous from your application. And this type is called sampling. and it can be triggered by timer interrupt or hardware counter overflow. Another type of trigger, it's an internal trigger or synchronous. So it is called from some event inside your application. And this type is called code instrumentation. It can be automatic or manual. We'll discuss more details about sampling and instrumentation in the next slides. And another dimension I would like to mention is how performance data is recorded. So there are two types. First one is a profile. Profile is summarization of events over time. So summary statistics about your application. And trace, it's a sequence of events over time. What is this exactly? I will also give you more examples and go more into detail what is profile versus traces and what are the advantages and disadvantages, and also the same about sampling and instrumentation. Let's first discuss technique, sampling. So first, let's consider, I hope you can see my cursor. We will consider this source code. We have a main function, and inside main, you can see my cursor, right?
Yes.
Okay. Okay, good. So we have a main, and inside the main, we have a for loop, and inside for loop, we have a foo function, which is called recursively. And here on the top, we can see the timeline of execution of this code. Each function is color coded in different color. Main is dark red. Foo zero invocation is orange, and so on. So basically, you can see the time is flows from left to right, and you can easily see how the application was executing. And to collect measurements about this application, we can apply sampling for this. And the sampling means that the running program is periodically interrupted to take the measurements. So, and so something like this, yeah. At a certain intervals, let's say every 10 microseconds, there will be an interrupt, and we'll get information from this point, and we can unwind the stack and see what was going inside the application at this point of time. There are different methods how to invoke timer this sampler, for example, with a timer interrupt or S signal or hardware counter overflow. But what you can already see that we get quite sparse information. We won't get everything about our application. For example, some information about tiny functions here and here will be missing. What it means, so with the sampling, we'll get a statistical information about program behavior. And not every single tiny detail will be covered at this. So that's why it is recommended if you use sampling to use a long-running application. It doesn't make sense to use sampling with application which runs for a couple of seconds. But if you run for several minutes, it is worth to use sampling. And the advantage of the sampling is that it's lightweighted. It can work with unmodified executables. Now let's compare sampling with the instrumentation technique. Again, we have the same example. We have the same main with the multiple foo invocations. And basically what instrumentation does, we insert a special hooks into for every event beginning on the end of the event. So like this. So basically here we implemented instrumentation. Before invocation of each function, we have an entry event and leave event. And they are also marked here in the source code. Of course, you can do it manually with the printf. I started foo or end of foo. There are multiple ways how you can do it. This is like automatic and manual. Advantage, you of course get full information about your execution of your application, but you can immediately also see that before and after that after we applied instrumentation, we have some overhead because measurement is not for free. You also lose a little bit time there, and it causes some overheads. Another disadvantage that you need to process your source code. You have to manually insert this enter and leave, so do it automatically. And the second, I already mentioned, this is overhead of the time, runtime. So here's an example how like the time samples will be measured. So basically, you'll get information about each enter and leave of each function, which is much more detailed in comparison to sampling. There are different instrumentation techniques. First is the static instrumentation. Program is instrumented prior to execution. So I already mentioned one. You can manually insert some hooks in your source code. You can enable some compiler flags. But you do it before execution. You can also link with a special instrumented library and so on. There are different techniques about this. And also you can use a dynamic instrumentation. Program is instrumented at the runtime. So basically you use LD preload technique to substitute some function calls, for example. And yeah, already mentioned, code can be inserted manually, automatically by preprocessor source-to-source translation. You can enable some compiler flags. You can use linking, or you can use binary write or dynamic instrumentation tool.
If I might chime in for a moment, the important thing to notice here, right, is for sampling, the number of measurement points is determined by the runtime of your application. And it's always the same on the runtime. For a certain runtime, you always get the same number of measurements, regardless of the application. So if you have application A running for 10 seconds and application B running for 10 seconds, you will have the same amount of sampling and thus the same amount of overhead. For instrumentation, the number of measurement points highly depends on your application, right? If your application A has many little functions, you will have a lot of measurement points, and thus a lot of overhead. For application B that only has 3 large functions, you will only have a very little set of measurement points and thus relative little overhead. So this is one of the main things you need to consider when thinking about sampling or an instrumentation type of tool. So what does your application do? Do we have many small functions? Since sampling is probably a better approach. If you have few big functions, instrumentation is a perfectly valid way to go.
Yeah, so instrumentation is also super sensitive. For example, if you use a C++ source code, where you have a insane amount of tiny get set operation, then the overhead of the instrumentation would be also insane. Yeah, we will discuss a little bit later what is the trade-off of what you can choose between sampling and the instrumentation, but it's like you have to test and see the overhead incurred by instrumentation or sampling. Now let's talk a little bit critical issues connected with any measurements. First one is accuracy. And intrusion overhead. Measurement take time and thus allows performance. So as you already saw in the very significant in the instrumentation that the measurement for tiny function or multiple function occurs as very significant overhead. And of course, it changes behavior or can change behavior. And your applications might deliver low performance as without measurement. Second is a perturbation. Measurement alters program behavior. For example, memory access pattern can change. We saw multiple cases when you enable a measurement that, for example, your server cannot converge anymore. We also saw cases when with a measurement, then it was converging, but without it wasn't converging. But it's rather like anecdote as a rule. but that what you need to know that the behavior of your application with the measurements can change from convergence to non-convergence and so on. Amount of memory usage will be also increased because measurement system also need memory. Then next critical issue is granularity. Here you have to consider how many measurements you want to run. Typically, what we recommend to do multiple measurements with a small amount of metrics rather than a single one with a huge amount of metrics. It's if you put more metrics inside, more counters, that the overhead will be more and more, and again, there will be intrusion and perturbation of your application. And that's why you have to consider how much information you need and how many measurements you need to do. Yeah, this is again trade-off of accuracy and expressiveness. So you have to tune up your measurements for your needs. That is accurate, and you get enough information to do some optimization. Now let's talk a little bit about measurements methods. First is profiling. Profiling, it is recording of aggregating information. What kind of metrics or information can be recorded? It's time, counts, for example, time spent in the function, in certain function, how many invocations of the function, hardware counters, cache misses, for example, and so on. And this aggregation is done across program and system entities. So basically aggregation across all function, call sites, loops, basic block, and so on. And of course, it's also does aggregation across all the system entities, for example, all MPI ranks and OpenMP threads. And profile is also provides statistical information about the run, man, mix, mean, and total number of values. What are the advantage of usage profiling? It works with long-running applications. Um, mm, but disadvantage is the variations over time get lost. We will get a example, but basically what you can imagine that you have a multiple iterations and behavior changes within this iteration, though you won't get what is going inside the iteration. You'll get aggregated information about this, so this information is lost. So profile, in short, profile is a summarization of events over execution interval. Now I would like to mention different types of the profiles. First one is a flat profile, which shows distribution of metrics per routine or instrumented region. And calling context is not taken into the account. So basically what it means, so after the measurements, you will get a table of some metrics and the values aggregated across call sites and call and system entities. But you don't see calling context. Calling context, for example, if you have a function foo and inside function foo we have a bar, we don't see this in the flat profile. So the calling context is missing. But if you would like to get this calling context, so then you should collect a call path profile. It shows distribution of metrics per execution call path. So in this case, you will see foo and bar. But of course, if you have a multiple invocations inside bar invocations inside the foo, they all will be aggregated. But if they will be outside of the foo, you will still see them. And there is also a special purpose profile, which is focused on only specific aspects, for example, MPI calls or OpenMP constructs, and where there you can compare processes and threads. Here I already mentioned briefly, but here is an example of profiling issues which are related to averaging. So first one is a moving bottleneck across processes. So let's discuss this. So each line represents a single, let's say, MPI process. So this is process 1. Time is goes from left to right, and we have a multiple iterations. This is iteration n plus 1, n plus 2, n plus 3. And inside iteration, and inside of each iteration, we have two different, let's say, function. Here, the green might be foo and yellow bar. In ideal world, we would expect that the green is equal and yellow is equal. So basically, they should be equally distributed here. But no. But here we can see that there are some moving bottlenecks. For example, here is yellow bar is longer than others here, but this bar is moving. And if we aggregate all this information, then our profile shows that we have an ideal case. Everything is balanced ideally, but this is not true. So this is not cannot be captured with profiling. Another case is below when we have an imbalance when it changes over time. So we'll see that the green bars are increasing. But of course, if we aggregate, we don't see it, that it was good, relatively good at the iteration n and n plus 1, but then it's become worse and worse. So of course, if we would like to get this information, we would like to collect traces about this run. And here's information about tracing. What is the tracing? Tracing is recording information about significant points. They also called events. Michael and I already mentioned a couple of times events during execution of the program. And what kind of events exist in the code? For example, it could be a function, loop, send, receive messages, and so on. So this is our events which we would like to record. And so we save this information is event record, so called, and in the record we save information about timestamp, where it was executed, location ID, event type, and additionally we save some specific information if needed. So advantages of the trace, it can be used to reconstruct the dynamic behavior. So for example, this changes within the iteration, we can easily capture with the tracing, and profiles can be calculated from the trace. So in general, we don't need profiles, but there is a very, very big problem with traces, that they can be easily become huge. So even with a short run, the traces might be become unmanageable, like gigabytes, terabytes of data out of a single tiny run of your application. And it's also traces can be also used for short durations or small configuration. You cannot run it with a super long run within hours or 24 hours. This is not possible. Otherwise, you will be flooded with huge traces, and it would be unmanageable to open and manipulate with them. So in short, event trace is a string of event records sorted by time. So trace is the abstract execution model on a level of defined events. So if we compare like very briefly what is the profiling and tracing. So profiling, can you imagine as a picture of your family with some aggregating information about your family, but tracing, it's more like a movie recording everything what's going on inside your family. Now let's consider some example with the trace, how it actually works. We'll have two processes. On the process A, we have a function foo, and inside function foo, we have a send, which is sent to process B. And whereas on the process B, we have a function bar, and the function bar has a receive from the process A. So, and this we would like to capture and also visualize later. For this, first we need to apply instrumentation. We add a special, we already know what is instrumentation. We add a special hooks inside. So for enter and leave for each function, for each event. Here is trace enter foo and trace exit foo, and the same for bar. And also we'll put a record for send. We want to put it before. We want to make sure that the send has started, so it's when it's invocated, and on the process B we put it after the receive, so we want to share that the received has complete. For simplicity, we'll imagine that it's MPI blocking call. Yeah. So this we done instrumentation. All these hooks were inserted automatically. Now we would like to measure. We run application and we collect information about timestamps and so on. For example, where it was sent, sent and receiver. If it's collective calls, maybe you would like to collect also information about communicator and so on. And so you'll measure time. You have to be careful about this, because timers on different nodes can be a little bit asynchronous. So maybe you would need to make sure that the timers are collected correctly. Now then we will collect per process, two different tables. First is a trace for process A, where we have a table. First column is the time when the event has occurred. Then we have a enter and leave events marked here, like all the events are listed here. And here we'll have a special column where we'll mention, for example, if it's a function foo, then we'll put it 1, and this ID will be listed in a separate definition file with all function invocations. So here, for example, we are calling foo, and the mapping is 1 to foo function, and so on. And here we have a send is happened at 62 time stamp 62. We have a send, and send sends to process B. And very similar to the process B, we enter all our events for enter and leave event, and also for receive. Also we'll have a definition table to map function invocation names to the ID number. Then we'll do unification. Make sure. Here I have to say that it's done virtually. It is not done on practice. So we'll have, usually when we collect a measurement, they will have a set of measurements on process A and process B. We don't do any merge, but for understanding, it's better to merge. So we will basically merge the definitions. All the definitions will be merged in a single table. Foo will be ID1 and bar will be ID2. Then we'll also merge trace A and B into a single one, global trace. It's again virtual merge, and we'll update all the values here to have a global trace. And what we can do with these two tables after that, after the trace is collected, we can visualize it, for example, or analyze it in some way. So here we have our global trace and global definition, and we would like to visualize this. So here I color coded all the function invocations, different colors. For example, red is a foo, blue is a bar, and so on. So we can interpret them and create a legend with the main, foo, and bar. So all invocation would be main, which is green. We can also create a graph with determined time steps. And so we can already mark our main as a full execution of our application. And then inside the main, we can already depict that our function foo happened from 58 to 64 time steps. So we can already draw it on this line of process A. Whereas our process B happened from 60 to 69 on process B, right? And we can already draw it. Then we can already put a dot at process A, which is sending to process B at time step 62. And receive has finished at 68 on process B, receiving from process A. And we can draw it with a direction. So basically, we can mark that when the send and receive happen. And yes, this is a nice visualization. There are multiple tools which support this visualization, but there are other possibilities what you can do with the traces besides visualization. For example, Skaliaska trace analysis detects some inefficient patterns within the trace, and so on. Now we know all the techniques like sampling, instrumentation, profiling, tracing, but when and which to use. And unfortunately, there is no silver bullet for this. There is no single solution for each. Depending on your task, you have to decide what you want to use. And here we have an analogy with gardening. For example, you have a garden and you would like dig a hole or clean from the snow your garden. Then you will use a spade probably, but nothing much you can probably do with a spade. Especially if you want to take care of your bushes, of your garden, you would need multiple small tiny tools like this for gardening. And if you would like to build a building, you would need a heavy equipment. And for the heavy equipment, typically we have no enough knowledge to use them. We would need some experts to use this. And very similar analogy is with the tooling and all these techniques which we, Mikhail and I described. You have to consider what is your need, what you need. So, so it basically means a combination of different methods, tools, and techniques are needed. For example, for analysis, you can think what kind of information you need. Is it statistics? Is it visualization? Do you need automatic analysis or data mining? The same about measurement. Do you want something like lightweight, but only sufficient at the long run? Then maybe you would need a sampling, or maybe you need a very, very detailed information about your tiny kernel. Then instrumentation is a way to go, where you can instrument almost everything and see a lot of information inside. Then again, if you need a statistic, then you would probably need a profiling. If you need visualization or additional information, how your court, how your application was running at time, then you would need a tracing. And also, sorry, instrumentation. You have to decide what kind of instrumentation you would like to use. Is it maybe manual? Maybe you would need to print Fs, and this is sufficient. Maybe you would need a source code or binary instrumentation, and so on. So think what is useful for you and your case. There is not a silver bullet at all. But of course, we have some recommendations for you, what can be used and what from our point of view is useful, and we are using mostly daily for the performance analysis. So first, we would recommend measure and analyze at the desired scale. So don't start with a tiny example. Prepare what is representative for your production run. Of course, don't run at the full scale, but start with the smallest but representative example, which runs for not very long time. Let's say if it's a solver loop, like it executes 10, 20 iterations, but like it's do some warm-ups iteration, but then after that it do something meaningful, maybe, yeah. Then we will prepare some short overview of different tools. Our personal favorites to start with is the Linaro Performance Report or Intel Application Performance Snapshots, which provides you as a basic information, how your application was running, how much spent in the computation, wall time, how much time spent in threading and MPI and so on. Very, very basic information, but it gives for you already a feeling if you have a problem, for example, if you have a CPU issues. In this case, you can also include other tools to use a low level profiler like LinarMap, VTune on Intel nodes, or UProf on AMD. If you think that there are some issues with the hardware, or you would like to investigate, then you would need to use other tools like Perf, Liquid, Puppy to collect some Puppy counters and analyze them later on. If you have significant time in communication, that is a good approach to use Skalaska or Vampire to see where you spend most of your time, to identify inefficient communication patterns and so on. If you use GPUs, use vendor tools. What is depending on your GPU, you might want to use NVIDIA Inside System, NVIDIA Inside Compute, AMD ROC M on AMD, and so on. So consult with the vendors, check out what is available, use it. For I/O issues, we highly recommend to use Darshan. This is simple but very powerful tool to understand issues with the I/O. Of course, you can use Alaska, Scorpio, Vampire, and Cube to do more or less everything what is described above, and we'll discover some of these tools on the next series. So the next iteration will be about how to use Scorpio, Alaska, Cube. And we invite everyone to participate. We'll give a hands-on example how to use those tools. And of course, if you need help, talk to the expert. They are always for you. They're available for you. Use local first level support. Use tools mailing list. If you don't know how to deal with a particular tool, you can always approach tools mailing list or chat channels. If you want a little bit more, if you want a hands-on approach with the tools, then I would recommend to consult with a VHPS tuning workshop. This is a bring your own code workshop series covering multiple performance analysis tools. The idea basically you bring your own code, and then the tool developers help you to apply tools to your application and later on analyze it. Another approach is to apply for the POP Center of Excellence analysis, where they provide performance assessment as a service, and this is a free service. I'll highly recommend to use this. And last but but not least is EPICURE. EPICURE provides support for performance analysis and debugging. So and of course, you can try all of this, and we highly recommend to contact, approach experts, talk to us. We'll provide you insight about tools or what you can, where you can apply for the help. Yeah, that's it from my side. Thank you very much. And now I'll give a time for questions.
Okay, Ilya, thank you very much, and Michael, for your very nice presentation. Now I think we have some time for some questions. You may send them directly to ask them directly. Feel free to open your mics, or then if you want, you may also put them on the chat. Okay. Maybe I have to ask some question, maybe not regarding this webinar only, because I think it's also introduction to terminology, to basic concepts on profiling our code. That's, I think it's very interesting learning how to do it. But can you tell us something? What will happen in the next webinars? How can we go deep dive in the performance analysis and debugging, so people can start joining us for the next webinars? As I think we may not introduce it correctly in the beginning.
The next webinar will be next week, same time, same day, Tuesday, 10 a.m.
But we have here a question, sorry, from Bennett.
Yeah, what is the
What?
process of initiating performance engineering support by EPICURE? So first requirement, you have to have your HPC computer project. If you have it, you can, there is a website where you can directly apply for the EPICURE support, or you can also do it during submitting the proposal to your HPC. This is the only way to apply for this. Yeah. For POP, whereas for POP, you can apply anytime. I think POP is COA is running until end of this year, and you can apply anytime. So difference a little bit between POP and EPICURE. So EPICURE provides a broader spectrum of work. So basically, it provides also debugging option. It provides porting. If you want to do some benchmarking, there are helpers which provide you help in this regard. But it also includes performance analysis and optimization.
Okay, so in the next webinars, we'll deep dive in this. This will be a series of 4 or 5 webinars that will end in July, I believe. So we would much appreciate if you can join us in this series, and we think it will be most useful for most of us. So join us next week for the next webinar. And Ilya and Michael, once again, thank you very much for your time.
Sorry,
There's another question? No.
There is another question, yeah, from Benik. So basically, yes, if you have your HPC project and it's active project, you can apply for this from user project, yes.
Yeah, as long as you have an Euro HPC allocation,
Yeah.
you are eligible to require EPICURE support. So feel free to ask support.
And if not, you can always contact us. We're happy to help you.
Yes.
Even if you're not part of your HPC.
Yes, of course. I think every supercomputing center will help, but if we can also use EPICURE support, it will be even better.
So as Ilya mentioned, so basically every compute center has a first level support. They know about the tools they provide and maybe have contact to tools developers. And we of course mainly focus on the users in Jülich, but we help others as well, especially in context of multiple European projects like POP or EPICURE. We have access to several systems, so we can have people on other systems as well.
Yeah, I just to complete, Michael, if you contact your first level support, everyone in the supercomputers will know all this kind of support that we have, and for sure will help you find the right way and the right help, or the most efficient help to help you solve your problem. So feel free to contact us, and you can enter by any operational center, and then we'll route you for the best project that may help you. Thank you for your questions. And some more question? Okay, otherwise I think we may end it up here. Sorry for the trouble